Thank you. So welcome to this seminar. So today I would like to take a different perspective on integrability. Now, integrability has proved to be a really fantastic tool, someone would say framework, in which many problems fit nicely and have a fantastic and wide spectrum of application, ranging from high energy physics, say string theory, condensed matter, statistical physics, and so on, and mathematical physics, of course. Now, today, I would like to take, as I say, a different point of view, namely asking question, how can I decide if a system is integrable? As a matter of fact, the question is undecidable. As it is equivalent to the halving problem of Turing. It's exactly the same. As well, I will ask question is, how probable is that you come across an integrable model? Are they really rare or really something that you meet, let's say, very frequently? However, being, first of all, an Italian, and second, having studied in Pisa, physics, I was taught along the line of Galileo and Fermi. What I mean by this is I take as a leading line, how to say, this word, in this case, formulated by Feynman, namely, it doesn't matter how beautiful we formulate our theories, our formulas, it doesn't matter how smart we are, if we not match experiments, probably is a nice fun, but nothing else. So what I want to say is I would like to stick our theoretical ground to something that describes nature. I have the pretensions to describe nature. Now, recent year, there has been, as a matter of fact, a stunning and very delightful matching between some marvelous theoretical work done on the realm of integrability and experimental work made by really incredible and skillful experimentalists. So nowadays, we have at least some set of matching between all the calculation done in quantum integrable model and experimental, at least quantum chain, but then there is cold atom and many other devices that one can think of. Now, of course, I cannot open this Pandora box like this. I have to focus. And I will just talk a little bit about a remarkable example, which is the Ising model in a magnetic field in 2 dimensions, which is a model that has been unsolved since the solution of Von-Sager. Many great physicists tried to solve it, including Young, but there was not much progress on this problem until in the late 90s, Sasha Zamolodjigo came up with a fantastic idea, namely, he took the point of view of the scaling limit of Ising model. I will be more precise later what I mean by scaling limit. And in this field theoretical limit, he was able to show that the Ising model and magnetic field, as a matter of fact, is a relativistic scattering theory, involve 8 particle excitations, which match beautiful the pattern of E8. The exceptional algebra. So this fantastic work has been done by Sasha Zamolodjigo in the, I think, 89. By the way, I was here in Santa Barbara at that time. It was a period of great excitement together with John Cardy and so forth. Years later, I exploit completely this matrix. This is exact. So we have the exact amplitude involving 8 particles. I took this data and compute exactly the matrix element of the spin operator as well as the energy operator. Now, these are made in terms of function, which is highly transcendental, elementary polynomial, but can be done and is computational very, very efficient. So this is the starting point. So if you want, this is the on-shell theory, this is the off-shell theory. Now, this, in short, the mass spectrum of the Ising model along the magnetic axis consists of 8 masses, of which you can compute exactly the ratio of them. except the first mass, which is just a measurement of the external magnetic field you are using. And these masses matches beautifully the linking diagram of E8, in which you really assign their position to the simple root of this algebra. Now notice that 3 of them are stable and 4 of them are unstable, in the sense of the above threshold, so they will typically decay. In this case, it's integrability which prevents this. So the spectroscopy of this theory is fantastic, it's incredibly rich. So you have all sorts of thresholds when you start putting multi-particle together. And I've been computing the correlators using the spectral representation of it, which is I take the, say, spin operator, I insert a complete set of states, which are these 8 particle and multi-particle. I use all the property of the spectral representation, and then you end up in a series which involve the matrix element, which are called form factor, and an integral on their, let's say, energies. So pictorially, it's something like this. You have the field, and they exchange a lot of particles in between. Now, to make the story short, we use this model and compare with an experiment that was done initially by a group in Oxford, Tennant, Poldea, and others that use neutron scattering. And more recent time, there has been the experiment has been done again with a great precision, and this is the result. So this I want to show. So this, the dot are the experimental curve, and the final one is the theoretical curve computed with the matrix element I gave. There are no fit parameters. No fit. Okay? It's either you're right or wrong. There is no other way. Okay? Now, I have no time to describe in detail this. I really refer to you to the original paper. There are a lot of things you can measure, the amplitude here, and so on and so forth, but I have no time. And I want just to stress this, because then we start my seminar, that I did this curve and this fantastic agreement putting only very, very few low-lying states. So this is the question I want to pose. How come that using just a few out of infinite many states, I can reach so high precision in my data? What are the bases behind? So this is what I want to bring you first along with me in the seminar. So at this point, I can switch off the things and erase and tell you what is the magic behind, because there is really some incredible magic behind this result, which as a matter of fact is generally shared by any two-dimensional models. So we can switch on the light. Okay, good. So let me once again. I will, in order to understand what's going on, we have to understand, first of all, the space of quantum field theories. Now, this provides for us a framework and a language that will be very useful to understand what's going on. I will discuss for you what are the experimental signatures, the more efficient one, that you can use to probe your theory. I show you one, but there are infinitely many, which are incredible precision, how to say, diagnosis of your class universality. And then I will tell you the remarkable property of two-dimensional functions, which, by the way, is the only measurable function that you can have. Higher order correlation functions, there are essentially no mean to measure. I mean, you compute it, but if you want to compute 4-point function experimentally, off-shell, not on-shell, off-shell, you don't know what to do it. So 2 points are essentially the only probe we have, but however are incredibly precise, and I will tell you this remarkable spectral series I was anticipating, and finally I will pose the problem, integral or not integral. That is really the question, how you can really find out if you are really handling some integral or not integral. Now, space of quantum field theory. So The formulation is pretty simple. First of all, you take a cutoff, let's say a lattice, or if you want an energy cutoff. You tell me the dimensionality of your space you are talking about. You tell me the group of symmetry you want to study. At that point, finding out the reducible representations and write it down, the most general monomial, which involve the order parameter in terms of the reducible representations. Okay? So if you want, this is the Wilsonian way of looking field theories. Now, example, pedagogical example for the sake of the seminar, Z2. The only representation is one-dimensional, real field. At this point, you write down the most general, let's say Lagrangian or action or Hamiltonian, how you write it, which involve derivative. Here I take just the lowest one, but if you want, you can take also higher. And the most general polynomial, which either respect or violate the group. At this point, you have an infinite dimensional space of coupling, and each point on this space define for you a field theory at that scale. It's an effective theory at that scale. Now, this coupling, of course, evolve. So, if you want to know what's going on, you just vary the cutoff. You compute the beta function, so the gradient, how they are moving, and then you study the flow in this space. You know a lot of property of this dynamical system. You know that they cannot cross except to the critical points. So the critical points are those in which the beta function are zero. At this point, under very general conditions, translation, rotational, and so on and so forth, you get conformal field theories. Now, conformal field theories allow you to do fantastic job, fantastic achievement, namely to spot the operator content which exists at the critical point. Okay? So you know which fields are there. In particular, you can identify those which are relevant. The relevant fields are those whose anomalous dimension 2 kappa is less than the dimension of the space-time you are working on. In general, a finite number of them. Okay. Now, when you have identified the relevant fields, this is really the starting point for the next analysis. Because you say, look, the ambitious goal would be to understand all this incredible space, the flow, if they are connected, if they are not connected, who is connected to whom, and so on and so forth. Now, this in general is really ambitious goal. Sometimes you can achieve something under some further information, say supersymmetry, just as one. But the more modest one, if you say, why don't let me study the vicinity of one point? Eventually extending to strong coupling later if you have means to do it. So the region nearby the fixed point, which is linear, you know, a normalization group is a set of non-linear equations if you start moving all the coupling. But the linear order, you have some kind of surface which are spanned by the relevant fields which exist there. So at this point, a very humble, how to say, a very honest way of studying what's going on around a critical point is to say, at this point I know precisely action. I told you, you can solve conformal field theory exactly. Let me default in terms of some relevant operator. Here I choose only one of them, but you can put all of them. What happens is, as far as you couple the system to a relevant operator, the system develops a mass scale. Okay? Either hidden or explicit. Namely, the theory can be massive, means this flow bring you, let's say, at infinity, where all the theory is completely massive, or can be massless, namely you reach a new fixed point in the infrared, but nevertheless you have a scale. So it's no longer a scaling invariant. Moreover, this flow can be integrable. Here I depict this in green, and this is part of the question here, or in general is non-integrable. So you have to deal with a generic quantum field theory with some bunch of excitations, with all the problem that this theory will have, namely resonances, the fact that you have production, the smart is completely crazy functions, and so forth. Now, the basic quantity of a field theory are correlation functions. Now let me focus on 2-point correlation functions. With this notation I mean the vacuum refers to the deformation I am using. It can be different if you change the deformation. And then I'm using some operators which I know exist at this point, imagining that they will persist at least in a region nearby. Okay? So this I call the 2-point function, the operator j kappa in the deformation I. Now, you can define, of course, higher correlation function. The point is, higher, as I stressed before, are difficult experimental problems. So let me focus on this and let me tell you how, nevertheless, you can reasonably say what has been done theoretically indeed coincide with the experiment. So I want to say that this quantity contains a huge amount of information alone. Now, first of all, I can use fluctuation dissipation theorem to relate integral of this correlation to generalized susceptibility. Now, susceptibility is you have a vacuum expectation value. Imagine you put your system in a magnetic field. You develop a magnetization. Then you take derivative. So these are the susceptibility. However, by fluctuation dissipation theorem, they always involve integral of these 2-point functions. Now, these quantities are dimension full. So once you extract the dimensionality of this constant, just tracing back the dimensionality of this field, blah, 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 the integral and so on, what happens is that you have some dimension full parameters and number. These are pure numbers. Okay? Now, my point is, in terms of this quantity, I can really provide to my friend experimentalist a telephonic guide, how to say that, he can check whatever he wants and conclude, yes, what I'm studying in my lab is this classical universality. Why so? Because usually we have been taught, we have been said that critical phenomena are characterized by critical exponents. And each class of universality has its own set of critical exponents. I want to draw your attention on the fact that these quantities are very bad from experimental point of view. Why so? Because, first of all, the critical exponents are usually algebraic function of the anomalous dimension of the relevant fields. But the relevant fields has a finite range of variation. So what I want to say is that if you go to Ising or tricritical or post model, you will find that this quantity, this is just an example, you have for a specific heat, for many, many others, you find that these critical exponents change really slightly, changing class of universality. Okay? Just intrinsically, because they are algebraic function, this number has a finite range of variation. Moreover, imagine that I want to check, say, if for Ising model this guy is 1. So I'm in my lab, I have my piece of material. What I should do? First of all, I should do a lot of work, and I should throw several decades of this, because I have to follow this behavior. Now, if your experimental friend is lazy, you're already dead. Okay? But the second point is, inevitably, they will have some error. And to spot this logarithmic scale, you have to trace a straight line. And you can put many straight lines compatible with that. I told you, a minimal variation, you will jump from one class universality to the other. So it's completely loose, completely, I don't want to say useless, of course, but it's not powerful. Okay? Not at all. And the same story repeats with many others. Now, what about what they call universal ratio? Universal ratio are quantity, this is just an example, in which you take generalized susceptibility and you start varying the various fields, take appropriate power, and then take ratio. These are pure numbers on which all of us we should agree, because they are really. But on top of that, these numbers depend incredibly from the dynamics of the theory, which has entered in, scrambled, and delivered the result. Because this guy, as we will see, is an infinite sum of intermediate states, which vary theory from theory. These involve couplings, and these are highly non-trivial set of numbers, and moreover involving integrals. So what I want to say is, you might enter here Pope and come up priest. You see? So is a number that you cannot predict at all. It is a range of variations which are enormous, and when you take ratio, the set of numbers that you find are completely different from class universality to class universality. And this provides an incredible telephonic guide to identify the class universality. Okay? As a matter of fact, this universal ratio are nothing else. You know that when you are nearby the critical point, the free energy, the singular part of it, it is written as a scaling function of the proper ratio of couplings. Now, if you start taking derivative of this number is probing exactly the derivative of this free energy, which of course is highly different from one system to the other. Okay? Now, let me just give you a very nice and beautiful example. Imagine you take the self-avoiding walk. Now, as a field theory, this is a ON theory, n goes to 0. As a matter of fact, this theory is integrable. You have all the scattering amplitude. I computed all the matrix elements of this theory. And what I want to probe is a universal ratio, which is very simple. Namely, if you have a self-avoiding walk and you have n steps, you can make an ensemble of open loops. So give me n steps, you can move around. Each time you move around another way. And you compute the radius, I think it's called radius of gyration, square, of course, because the average of R is 0. This one scale anomalously with a term which is dimension full according to the lattice where you are. Now, the same story happens if you take closed loops. Exactly the same, should scale in the same way because they have dimensional are the same, but with different constants. Now, if you take the ratio, this is a pure numbers which characterize the class universality of the. Now, if you do this calculation for ON in the way I told you, you find number 13.70, which match beautifully with all the lattice simulation you can do, changing the lattice. So if you do triangular lattice, people have found by Monte Carlo, which is 13.69. You take square lattice, I think it's 1370. Right? Okay. Moreover, for Brownian motion, this ratio is identically 12. And this 12 comes because these correlations are integral of Bessel function. So if you compute exactly, this ratio is 12. Now, 12 towards 13.70 is a great 10% at least variation. Anyone can be able to start. Okay? Now, this is somehow the philosophy behind. I have to tell you this mystery. The mystery is how come that I use my spectral representation with very few particles and nevertheless get astronomical good result. It's a mystery because, as a matter of fact, I should put here an infinite sum. So you might ask, what you told us is beautiful, but how the hell you are going to handle this sum? Sum and integrals. Now this is the real novelty. Real novelty is like this. Now, if you have a correlation function, 2-point function, here I am momentum, you insert a complete set of states. At this point, you can represent this correlation function, the so-called spectral representation. What it is convolution of free theory, because you see this is the propagator of free theory of mass m, but with a density that you have really m squared. So the point is, what is this density? This density is a sum of all the n particles, an integral on the invariant measure of the theory, which typically is this, the delta function between all these particles beyond shell, and the matrix element. Okay? So it's a complicated object. Something that a priori, how to handle this? Let me take the Fermi attitude. You know what Fermi did? Any problem, you just reduce to the basic. Get an answer and then try to refine it. Okay? Let me take exactly the same attitude. Imagine I say, look, these objects are complicated. The form factors are complicated, are highly transcendental functions, satisfy the recursive equation, are kind of heavy work. Let's pretend I do not know this, namely they are 1 for any particles. Okay? Can I estimate how my density is growing? Why so? Because you expect on a general ground that this density should vary smoothly as far as you do not meet a threshold of some particle states. When a new threshold opens, this guy should have a jump, and then a jump, and then a jump, and so on. So this means that if you truncate the series to a lowest number of particles, generically, you're going to make a big mistake going to high energy. High energy means short distance. Okay? And so this is a problem. So how come that this will not happen? Well, the story is this. Let me evaluate the phase space alone. Also, this evaluation is complicated. You have to do the Laplace transform and analyze this. But you can do easily in 2 limits. The threshold, Tm, and when the energy is infinity. This can be easily evaluated, this Laplace transform. Now, when there is a threshold, the phase space is at zeros of some order, which depend on the number of particles and the dimension of space. Okay. What about S infinity? Now, S infinity has a dependence on the number of particles at the dimension of the space. So, for instance, if you are in 4 dimensions, the phase space of n particles grows like 2n minus 2. Okay? So you have no way, and this is the reason why people never use spectral density to evaluate anything in 4 dimensions, because the phase space grows enormously, depending on the number of particles, and immediately you are off any approximation you can have. Immediately. Now, what happens in 2 dimensions? In 2 dimensions, there are 2 miracles. 2. The first is that at high energy, you see, this is the magic d minus 2. The things drop, and the phase space shrinks. So, more energy you pump in the system, more shrinks is the phase space of the particle level. At this point, you have to evaluate more carefully, and there are logarithmic involved. So the phase space at high energy shrinks with logarithmic correction. By the way, this logarithmic correction is at the origin of the Regge behavior of inelastic scattering in 2 dimensions. Because if for the form factor I put a factor alpha and I resum them all, I have a power. Okay? So the phase space shrinks. And now, what happens if now I include the form factor? For general property of integrable model, this form factor should have zeros of higher order at each threshold. So, in conclusions, my spectral density here will acquire here a power 3, and at high energy will shrink. So it's a function that is no way it can grow. There is no way, because asymptotically it has to decrease. When I write to the threshold, it tries to increase, but there are zeros of higher order. So before overcome the zeros, is already died. So at the end, the spectral density generically in two-dimensional theories is something like this. And if you take, let's say, two-particle approximation, when you arrive to distinguish the difference with the actual one, you are already tired. Okay? So the difference starts to be sensitive at astronomical energy scale. So the combination of the two allow me to truncate the spectral representation to lowest order of particle. At this point, getting nevertheless an incredible precision of many values on the energy scale. Okay? So this explains one thing. Now I cannot resist to tell you a trick which also combines integrability with this kind of things, which is this. Now the spectral series is in two dimensions, is something like this. With the rapidity of the particle. Now you see this series is very efficient for large behavior of the separation because it's a series in exponential MR. Okay? But nevertheless, it's an exact series. We know that this, guys, for R goes to 0, has to be a power law with some critical exponent. And the question is, how I can get a power law out of a series which is of exponential, and moreover, can I connect the form factor to these values? There are a beautiful trick to do it. The trick is, imagine that you close for a minute the eyes and imagine that beta are a coordinate or a fictitious gas. So this is a gas, a one-dimensional gas or rapidity V1, Vn. And this expression reminds very closely the grand canonical partition function of a gas, with one basic difference, that the fugacity of this gas is coordinate dependent, because it's this one. So the fugacity is this function, 1 over 2 pi exponential minus mr cos theta. And how is done? When r is going to 0, is a function which is constant over a range 2 logarithmic 1 over r, and is height 1 over 2 pi. And after that, there is a double exponential decay. So this means my gas effectively lives in this range. What is the equation of states of a grand canonical partition function? So a grand canonical partition function, the equation of states is exponential. The pressure is a function of the fugacity times the volume, but the volume is logarithmic. So this is 1 over mr p over z. So if I solve the pseudo-thermodynamic of this fictitious gas with interaction given by the form factor that integrable theory provide me, I know the enormous dimension. Okay? Now if you do this job with a model that has been solved in this way, the nice thing is that this pressure turns out to be a rational number. So if you do for Ising, this form factor are just product of hyperbolic tangent, so relatively easy. By the way, this provides an integral representation of the famous Parlevin for Ising. But if you solve the thermodynamic of this gas in this specific way, you find that the pressure of this fictitious gas coincides exactly with 1/8, the number of Ising Model. So there is a very, very nice matching between massive data, massive correlation, form factor scattering matrices, and ultraviolet. Okay? Are there any questions on these points? No question. I would like to go to the last part. The last part is I'm addressing the question: if I gave you a model, or if you want an equation of motion, whatever, I mean a way of defining a theory, if you have a way of deciding if a theory is integrable or not. Now there is a joke on that. There was a famous mathematical physicist, Hirota, that had been worked a lot on integrable model, Hirota equation, Hirota set of equations. So the joke is you have something on your hands, you want to know if it's integrable. You write to Hirota, and if you do not hear in 1 week, okay? I want to say this question touches a very serious one. If I give you really an equation of motion, is this an integrable theory? If I give you this equation of motion, is this an integrable theory? As a matter of fact, you do not have waves, okay? A priori. So why so? Well, first of all, the definition of integrability that is given in classical mechanics, Liouville, so any integral of motion associated to n variable, in quantum mechanics fails, or in any case is not enough. Because there are a lot of subtleties. For instance, you are looking for operators which compute with the Hamiltonian. Yeah, but in quantum mechanics there are all the projectors. So there are infinite of them. So does this mean that any system is integrable? Of course not. So there are a lot of subtleties how you define an integrable model. Now for my purpose, I will define an integrable model as those which are supported by a set of local charges, can be also semi-local or non-local, but let me just be simple. Namely, something that can be derived by some densities, local densities, which in complex coordinate lie by this, and they satisfy this conservation law. Okay? Now, S label my conserved quantity. If you want, it's like a spin, or if you are really dealing with some Lagrangian theories, the higher order of derivative you are trying to look for conserved quantity. Now, by the way, the spectrum of S can be extremely interesting. For instance, a spectrum of S plausible is this one. Or can be another one. So this is for the Ising magnetic field, this is for the tricritical Ising in temperature, and so on and so forth. I want to say the spectrum itself is a very interesting problem from many perspectives. Anyway, so this is my definition of integrable model. I define integrable model if it's supported by a set of conserved quantity compatible with the equation of motion. Now you understand why it's impossible to decide a priori if a model is integral or not. Imagine that you have tried hard to find conserved quantity up to the spin S, and you didn't find it. How can you be sure that it doesn't exist S plus 1? Of course you cannot. Simply you cannot. And so you are really in the same situation of outing problem of Turing. You try, you never succeed, but you never know what's going on. Now, as a matter of fact, this question in the pure realm of mathematical physics, non-relativistic theory, and so on is undecidable. The only way you can make progress is if you take the point of view of relativistic field theory. Why so? Because the conservation of this type imply the conservation of an infinite number of conserved quantities which involve higher power than momenta. So if you have a scattering which involves n particle, in addition to have the usual conservation of momenta, there are associated to this one conservation of higher power in the momenta. And when you are in presence of this higher power, this prevents any kind of production or annihilation process. At this point, we have a very computable way of deciding if a theory is integral or not. We just compute the Feynman diagram, and we see whether there are production or not. And this can be used as an integrable sieve to spot which are the theories which are integrable and which one are not integrable. Okay? So this is the simplest criteria. Now you might ask, and so what about relativistic or non-relativistic theory? Can I make any progress on that? Yes. As far as you classify the relativistic one, any field theory contains two parameters, velocity of lights and constant, Planck constant. Once you have obtained a classification of integrable relativistic theory, you just have to re-establish the presence of C and H and take the appropriate limit. In this way, you can hope to classify also non-relativistic and non-classical models. Okay? Now, if you do so, I've been doing so exactly in this way, I obtain an incredible result that in non-relativistic theories, the only quantum, the only integrable models that come up is the nonlinear Schrödinger equation. There are no others. So the nonlinear Schrödinger equation is, is a theory, is a non-relativistic field theory, which is associated to this so C is the wave function. So the only theory which is integrable is if kappa is equal to 1.
What about the lambda Lipschitz theory?
I don't think it is. Probably it's not. It's not. I don't think it is. There is no way of getting this.
Not integral?
Well, I was too fast. I have to say I was too fast. Namely, let me tell you what I'm trying to do. I think I can spot the ones you're talking about. So, in order to obtain kind of classification, you should establish some criteria, of course. Imagine when you say, I want to classify a group, you have to tell you compact, non-compact, finite, non-finite. So I have to establish some criteria. The criteria I want to establish is relativistic field theory according to the manifesto put forward by Veltman and Toft in 1974, which is called diagram R. Diagram R means a field theory is defined fully by Feynman diagram. There is no hidden sector. At this point, you decide how many fields, say boson, you want to have, and then the group, and then you write the most general Lagrangian with that. And so on and so forth. Okay? Now, what I'm referring is theory which I can derive from this, and from there come the nonlinear shape. You can take the point of view to start from nonlinear sigma model at this point. That might be this point. I didn't come across precisely, but I cannot use this framework to answer the question. I have to say, depend very much on your starting point, what you want to classify. Okay? So, if you take this starting point like this, what you have to do, the integrable sieve will consist of the following way. Write it down, all the n amplitude nm, which is all bunch of particles like this. First at the 3 levels, and then impose to be 0. Okay? At this point, you identify certain bare value of the mass and the couplings, and then you will see if these values will survive the renormalization. Now, fortunately, in 2 dimensions, renormalization are either of infinite contribution, which are just ample, but these are somehow easy, but then you might have a finite renormalization, say for the mass diagram like this. So you have to be sure that the value you get at the 3 level satisfy also the renormalization. I want to just present a simple example, which as a matter of fact has been worked out by Patrick Dory, which actually established also this way of thinking in classifying the integrable model. And then I will not enter in much detail because Davide Polvara, which should be somewhere, is here. I think will make us enjoy this story because he's working exactly on this and will tell us the story, how it goes for higher R. So I'm just presenting the simplest calculation which involve one field. So imagine that you have 5 to the 4th. You want to ask, is 5 to the 4th integrable? Now, in order to conclude that it's not integrable, it's enough to find one process. So imagine that you want to spot 2 which goes in 4, having this. So you have this kind of graph. Okay? Yeah. Now, if you compute this graph on shell, remember in 2 dimensions everything is a mass, is number. So what you get is I m squared G4 squared over 32. This you get minus I m squared G4 squared divided 96. The sum is not 0. So there are production. Landau Ginzburg 5 to the 4th definitely is not integral. Because I found a process 2 which goes in 4 which violated the charges. So how I can make this integrable? I can add a 6th term with appropriate couplings. At this point, if I have possibility of adding a 6th term, G6, and then you can make all the things coming from combinatorics. At this point, you have a condition. The condition is the sum of all these graphs is I 48 G squared 4 minus G6 m squared. So I can kill this amplitude as far as G6 is G4 squared. And this story can keep going. This is what Davide will tell us in the future. So to make the story short, to annihilate at the 3 level all these graphs, there should be a relation between coupling at arbitrary order, which is given by this. If you resum the total Lagrangian, you obtain only the Sinch-Gordon model. It's the only theory integrable with one field. Okay? The only. There are no others. Now, with this, if you take the limit, you obtain the linear only. Okay? That is. But if you start with nonlinear sigma, we did also this analysis, but here I don't want to. So this is the starting point. Now, what happens if you take arbitrary R, the num here?
The question.
Yeah.
I was just asking, what happens if you include the cubic term?
Yeah, yeah.
And what you get.
Thanks for the question, Mina. So I decide here to pose the problem. Are there integrable model with one field which is Z2 even? Sich Gordon. If I put the odd term, you end up in the so-called Bullock-Dot model. So if I include here the cubic term, of course I'm forced to get the fifth, the seventh, so on. There is, indeed, this goes, there is a unique model, which is called Bullock-Dot model, which is this. Only one.
And what happens in the non-relativistic image for this?
What happens?
In the non-relativistic...
all become linear. All.
Okay.
It's incredible. Indeed, the story is even much interesting because I've been pursuing the way of classifying this for arbitrary R. The problem gets immediately out of hands, so you can do really some example. And I corroborate my analysis with an alternative method which you use directly as matrix and bootstrap of that matrix. Now, inevitably, whatever you do, the only model that you find, according to the diagram R philosophy, is field theory which are of the Toda type. And so with this, is the last things, and then I will close my seminar. What are the Toda field theories? You take an arbitrary thinking diagram, simply laced. Say you take E7. You add the extra maximum root, which is also a root of the thinking diagram. And then the total field theory are theory which involve a number of fields equal to the rank of the algebra. So this plus some y exponential. Where Q are integer number uniquely defined by the algebra. Right? So these theories are fully defined by the simple root of your algebras. And apparently, when you do this integrable sieve, it's the only theory which survives it. There are no other theories. Okay? And if you take the non-relativistic limit, obtain just the decoupled ones, half decoupled limits. So I will close here because I think at least the main idea I want to convey I gave. The rest are technical problem. In particular, I can also estimate the number of theories that you can get. It's exponentially large. So if you find some theory which fit, it looks like very, very close to the so-called NP complete problem in computer science. And to spot the solution is incredibly difficult. You have to check many, many millions of Feynman diagrams. But if I gave you a solution, you can immediately check it works. So, thank you very much.
More questions?
Yeah.
So there, when you required vanishing of all the processes, why do you require it them only to vanish at 3 levels? That you also need.
Yeah, it's very, very good question. So it's a kind of how can I say, methodological approach. Namely, you have your amplitudes in general, full glory. So what you do is you first see if at the 3 levels something happens, because the 3 levels are just equation, algebraic equation, complicated one. Finding a solution is already a miracle because are highly nonlinear, the propagated masses are downloaded, the Kavli are coded, and so on. Imagine you find this. At this point, what happens is that if they are verified, there are very specific ratio of the masses. Say one mass has to be golden ratio of the other, in such a way to cancel. Now you are hoping that the renormalization will not spoil the ratio of these values. Will move the values, but not the ratio. Okay? So this happens, for instance, for the non-simple list. If you do the 3 levels, you get a certain number of masses. When you dress them, the range of the mass exactly remain the same, all move the same. So this is the only way you can get integrability, if you think. Because if at the tree level you find something, and then you start putting correction, there is no continuity in these equations. Are Diophantic equations, but there are no small parameters you can play with. You see what I mean? So as to survive only as an overall rescaling. Otherwise, the theory is not integral. So this is why it's exponentially rare to come across an integral theory. I can compute the number of theories which come up with a certain number of. You will see they are exponentially large, but only few survive.
Yes.
I have two questions. One is, how can I understand that n equals 4 super young means is integrable in
No
this way?
idea.
Okay, maybe it's a fair question.
Actually, I would like to ask you.
The question is, what about, I mean, I don't know, what about spin chains? Can I have some criterion like that?
It's a good question. I'm afraid not. I'm afraid not. Doesn't mean that you have, you know, the integral system we are familiar with is because we are familiar with. Someone else has worked it out, I don't know, the R-matrix or whatever, the way of solving them. But if I come to you with a spin chain of something, and I ask, is it integrable? No idea. No idea, really. You do not have a criterion.
I'm not an expert, but it seems that people diagonalize the Hamiltonian and they look if there is repulsion of level or not.
This is an experimental criteria, which I also use very often, but is an experimental criteria with all the kind of things. So what Vincent is referring to is that if you have an integrable models, you can look for the energy levels. You can diagonalize them numerically. At this point, look the gap for these energy levels, and you plot the probability that exists certain gap. So you do the histogram of this gap. Now, the story goes that if the system is integrable, this gap follows a Poissonian law, namely exponential minus s, meaning you have high probability that there is zero gap, so level cross. And this level cross, this highly degeneracy, is associated to presence of symmetry and so on. If on the other hand you observe that this gap repel, so the probability that they cross is zero, you say there is nothing which allow me to. So it's beautiful criteria. Numerically, is the however is first of all you have access always to finite number of levels. To distinguish a small gap from a real crossing is a problem. And namely, then you have to do a statistics. So I did for several models. What you find is a confirmation, if you already know is integrable. So you find that, wow, the things satisfy Poisson. But if you didn't know, you want to spot it, if it's integral, I think there is question of resolution, which energy you are using, and so on and so forth. So it's not a clear-cut criteria. It's a nice, but it's not clear-cut.
Sorry? Okay. No, sorry. One here and one over there.
Do you know any example, or at least can you imagine a theory which is partially integrable? Maybe the number of conservation laws is smaller than...
Thanks for the question. The answer is yes. The answer is yes, yeah. So what can happen, so life is complicated, right? So what can happen is you have a huge Hilbert space, a huge Hamiltonian, where some subsector are integral, but not in total. I have explicit example. I can give you, it's a bit technical, but I can give you. It's essentially a system made of colors, species of particle, with interaction which depend on the color. And now what happens is that a subsector in which there is only one particle repeated many, many times in the ocean of all the other different is integral. So the scattering of this particle with all the others satisfy Young-Baxter and so on. But if you start putting many extra species, it's not. You have a explicit violation of Young-Baxter. Yeah.
Another question. Yeah, just a curiosity. What about long-range models?
I have no idea. No idea. Actually, I mean, once again, it's fully interesting. As I said, I have to establish a criteria. You see what I mean? When someone told you, I classify this, you should ask according to which criteria. Long range, unfortunately, does not follow in the scheme of relativistic theory because it's not open. So at this point, I cannot write down, how to say, I cannot define a theory through the Feynman diagram. I need something else. Doesn't mean that it cannot be done, but it's a different story. Okay, so indeed, this is the first seed in a beautiful subject which remains to be explored in detail.
I think last question.
So I was just wondering, in this picture, it seems that everything is very rigid, but you can also consider deformations of integrable models, and you can have parameters in there, right? That would be like you start from sigma models, and you do, for instance, all sorts of quantum deformation, other deformation that they've heard in the program. So how do you see this in this more bootstrap or diagrammatic approach, the fact that you have these parameters with different
I think you don't, I mean, I can put it if I want, but it's not the spirit of the exercise. You see, because what you're referring to, this dressing, the TT bar and so on, are irrelevant operators.
No, also things like squashing, for instance, if you have sigma model and on the sphere, you squash the sphere, you can do it in such a way that
Depends on the starting point. If you start, I also analyze sigma model, we can discuss later. If you start with certain framework, you get only result in a certain framework. If I start from sigma model, the most general sigma model, I might get something else. So there might be, I discuss something in the ON context, for instance, and I arrive to certain results. So depending on the starting point, what is the starting point and which rule you're applying.
Okay, thank you very much.